Hi there. Thank you for clicking on this video. This lesson is about the roots of polynomials. Please like this video if you find it helpful, leave a comment or ask a question, and check out the practice set for this lesson as well as the other videos that are on the channel. We want to start off by establishing what are roots. So if you are asked to find the roots or identify the roots, or simply you're discussing roots in class, what exactly are we talking about there? Well, we can define roots as the values of x for which the function is equal to 0. Now, there's an alternate vocabulary word that you will hear, and that is zeros. So literally everywhere that I am using the word roots, you could use the word zeros, and I would say that they are about 50-50 in terms of which word is used. So some textbooks are going to say the zeros of polynomials or find all the zeros. Others are going to say to find all the roots. And the same with your graphing calculators. Some graphing calculators, you're going to look in a menu and you're going to pick zeros. It'll be zeros in the menu. Other graphing calculators, you'll be looking for the word root. So while I am using the word roots in this video, I actually in my classroom will use both words, and I try to use them both pretty interchangeably so that my students don't get too used to only hearing one of those words. They are both used, okay? So they are the values of x for which the function is equal to 0. Now, the x-intercepts are roots, but they may not include all the roots. So just so we can be clear about that, if you have your xy plane, okay, so we got our xy plane there, and we have some kind of graph on it, okay, if you look at your x-intercepts are where your y value is equal to 0. And of course, we know that like in a function, the y is the f of x. And so we know that where there are x-intercepts, those are zeros, but they might not be all of the zeros or the roots that a polynomial has. Now, there's a theorem. It's called the fundamental theorem of algebra, and I'm going to give you a user-friendly version of it. The number of roots of a polynomial is equal to the degree of the polynomial. Now, I did a little bit of research before I started to record this video to see like how feasible would it be to kind of go through a proof of this so that this isn't this random factoid that you're just getting in a video. The proof for it is really beyond the scope of the course and definitely beyond the scope of a 20-minute-ish video, 20-25 minutes. I don't know how long the video is going to be, but however long the video is, it's beyond that in terms of something that we want to cover. So for now, anyway, you just kind of have to take my word for it that the number of roots of a polynomial is equal to the degree of the polynomial. Now, we have an asterisk here. This includes complex numbers and roots with multiplicity. So when we say the number of roots is equal to the degree, it's not just the x-intercepts that we're looking at. It's also going to include things that do not show up as x-intercepts or things that might be in a polynomial that count as an x-intercept more than once, so to speak. Okay, now what we're going to start off with is looking at some examples with real roots because real is usually a good place to start. It's a little bit simpler. And so with this first function, this is a linear function. The highest exponent in that function is 1. So this is degree 1. And that means we're looking for one root. Okay. Now, the definition was the values of x for which the function is equal to 0. And so I'm going to take my f of x there and plug in a 0 and then simply solve the equation. So I will add 1 to both sides and divide both sides by 2. And we get x is equal to 1/2. That is the root. Now, so you can see what this looks like on the graph. Let's take a peek. And there's the graph there. So you can see there's the function f of x equals 2x minus 1. And here's the graph of it. And there's the x-intercept. And you can see the x-intercept is 0.5, which we know is the same as 1/2. That's the decimal equivalent. And so you can see that by solving it, this would be your algebraic way of finding the roots. And then you can also graph them and you can see, yep, that line has one root. And you can tell there's no more roots to it because the line's going to keep going forever to the left and forever to the right. It's going to keep going up and down, and that is the only root. So you don't think, oh my word, that line is going to have more than one root. Now my next function here, this is a quadratic. The highest exponent is degree 2, and so we are expecting this to have 2 roots. Well, we can plug in the 0 there. And now we are in a position to factor. Now, in this video, I am going to operate on the assumption that you know how to factor. If you need a factoring review, we've got several videos on the channel that go through how to factor, and we do the area model. I've got some comparison contrast videos, things like that, where you can go through how did I just do what I did there. Now, we can use the zero product property, and we know that that means x minus 5 could be 0 or x plus 3. Adding 5 to both sides, we get x is equal to 5, and subtracting 3, we get x is equal to negative 3, and those are the 2 roots. Those are the values of x for which the function is equal to 0. So let's take a peek at what that graph looks like. And there it is. Now, I chopped this off just for the sake of space. I didn't want the graphs taking up this huge chunk of the screen here. But this is a parabola, and I could have like snipped off more of the parabola there, but it is a parabola, and you can see once again, we've got those x-intercepts with the -3 and the 5. And because we know what parabolas look like, we know that it's going to keep going up forever. There's not 3 roots or 4 roots or anything like that. Okay, so we see like degree 1, degree 2. We're going to do one more. We're going to take a look at this one. This one, the highest exponent is a 3, so this is degree 3. And so for this one, I am expecting 3 roots. So I'll plug in the 0 for the f of x. And for this one, I'm going to use factoring by grouping as my strategy. So I'm going to take my first group here, and then we have the second group. In the first group, I'm going to factor out an x squared, and that'll leave me with x plus 1. In my second group, I'm going to factor out a -4, which is also going to leave me with x plus 1. Now, if I kind of lost you there, okay, you can check out one of the lessons on factoring by grouping to see how this works. There's also some other ways you can visualize it, but we've got x squared. If I distribute this, this would be x to the 3rd plus x squared. -4 times x is -4x, and -4 times 1, positive 1, would give you the -4. Now, what we have here is another common factor. I see that this term here and this term here share a factor of x plus 1. So I'm going to go ahead and factor that out, and that's going to leave me with x squared minus 4, which is a difference of squares and can be factored into x plus 2, x minus 2. And now we apply the zero product property. So I have 3 things multiplied together that give me a 0, which means at least one of those had to be a 0. We'll subtract 1 from both sides to figure that one out. We'll subtract 2 from both sides to get that, and here we'll add 2, and lo and behold, shocker of shockers, we have 3 roots. Okay, 3 values of x that will make that polynomial equal to 0. So let's take a look at that graph. Okay, so as we add the degrees and we kind of add these like bumps going around, and you can see that we have values at -2, at -1, and over here at +2. So we definitely have this connection between the algebraic, like solving the equation when it's equal to 0, and what we're seeing on the graph. Now, this is where it starts to get a little weird. So if all of my roots were real numbers all the time, then this would work out nicely and we wouldn't need any other kinds of strategies. We could just graph them all and see what the roots were. But what about this one? Now, for this one, this is also degree 3. So we are expecting 3 roots. And so we'll start off the same way. Now, for this is what's called the sum of cubes. And I have not, at the time I'm recording this, posted a video for how to factor the sum of cubes, but it is like the next thing on my list to record that. So probably, unless you are watching this like the very first week that I upload it, I actually, it's Labor Day this weekend, so probably I will take Labor Day. So unless you're watching this video in like the first 2 days that I have it up, you should see a sum of cubes video that you can click. It should be right on the same playlist, like a video above or below. Okay. So this factors, at least the way I teach this, is with something called a SOAP sandwich, which sounds weird, but, and we learn that when we are factoring the sum or difference of cubes, we have like a small parenthesis and a big parenthesis. And SOAP stands for same, opposite, always positive. So if it's a plus sign, we start with a plus sign. Opposite means our next operator is a minus sign, and then always positive means that my last operator is always a plus sign. And then we take the cube root of each of these. So we ask, what cubed gives me x to the third? Well, that would be x. What cubed gives me 8? That's 2. And then the sandwich part is square it, smush it together. So we take the x, we square it, we take the 2, we square it, and that gives us like our loaves of bread, or not loaves, but slices, I guess slices of bread. And then the filling on the sandwich is like a PBJ. We're going to do x times 2 and get 2x. Now, there's a formula for that you can memorize. I think this works just as well as just memorizing a formula. You just remember a SOAP sandwich. If you try to use AI to do this, if you try to use like Gauth, it does some wild stuff. So do not recommend. Okay, just like stay away from it. So now we've got the zero product property again. So we have x plus 2 equals 0, but then we end up with this. Okay, so we end up with a quadratic. Subtracting the 2 gives us the -2, but over here, we have a little bit of a problem. So you might try to factor it. It actually does not factor. And so we have to use the quadratic formula, which is the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So we've got the opposite of b. B is -2, so the opposite of -2 is +2. -2 squared is 4. Okay, so -2 times -2 is +4. Minus 4 times 1 times 4 all over 2 times 1, which is just 2. This is 4 minus 16. And we end up with -12. Okay, so now we've got to simplify the square root of -12. Well, I'll do a little bit of scratch work over here, okay, because this kind of moves quickly. So this would be -1 times 4 times 3. The square root of -1 is I, the square root of 4 is 2, and then the 3 would stay under. So when I go to write this here, I'm just going to switch the order of the I times 2, and we're going to do 2I root 3. And then what I want you to notice is we got some 2's there, okay? And those are going to cancel out, leaving me with 1 plus or minus try that one more time. I root 3. Okay, so the 3 roots are this. We've got a real root at x equals -2. We have a complex root at 1 plus I root 3. And then we have another complex root at 1 minus I root 3. Usually it's going to be written like this, okay? Usually we would not split it up. We would keep the plus or minus in it for efficiency reasons. Now, as we look at that, I do want you to notice something about the complex roots. When you are finding complex roots, you're always going to have this plus or minus coming out of your quadratic formula, and it means that your complex roots are always going to dump out in pairs, and they're actually going to be conjugates of each other. So you're going to have something plus something, and then you'll have the same thing but with a minus sign, and that's always going to happen because of the nature of the roots. Okay, so that's a helpful fact. So let's take a look at this one with the graph, okay, and see what we see. So on the graph, I can see that we do have the x-intercept and we're able to see the real root. But then in this one, where like if you rewind the video and you look at the last one kind of had this dip and it came down and crossed again. This one, it looks like it's just kind of leveling off. If it's dipping, we can't see it. But the little, like, I don't know what's called, like a little bump in my cubic is floating above the x-axis and it's not generating any more zeros. That's how we know that our other two zeros are complex. So in this one, we have one real root and two complex roots. And remember, those complex roots are always going to come in pairs. So if you're doing a multiple choice test and you see an answer choice that only has one complex number, like you would not pick that. Like that will not ever happen. They're always going to dump out in pairs. All right, now let's take a look at this one. So we're exploring like some of the weird things that can happen. So this is degree 2. So we are expecting 2 roots. Well, this one is factorable. So I set the function equal to 0, and this one I can factor, but what happens is I get the same factor twice. And so we can have x plus 2 equals 0, and then we have like this duplicate x plus 2 equals 0. Normally, when you're just solving a quadratic, we don't bother writing it twice because there's only one, well, the answer here is -2. There's only one -2 on the number line. So once you have that number as your solution set there, you would not write it again. But it does appear twice. And this is called multiplicity of 2, okay? Meaning that the result is showing up 2 times. So when you're stating the 0 or the root, you might say a root of x equals -2, and then you might see something like a times 2 or the word multiplicity of 2, and that's indicating that it is appearing twice. Then you can actually have things where a root appears 3 times or 4 times, like you could have it appear as many times as you want. You probably won't see that. Usually it'll just go up to a multiplicity of 2, maybe 3, but like at some point, like, you know, we're just not going to bother anymore. So that is the other little hiccup, that when we're talking about there being 2 roots, we do take multiplicity into consideration. So let's take a look at the graph. So this is my parabola. You can see the -2, but what I want you to notice is the graph is just bouncing off of the x-axis. So I've used the word like it's touching the x-axis or is it bouncing off of the x-axis. When you see that happen, it means that you have what's called even multiplicity, okay? And usually the even multiplicity means it's multiplicity of 2. It could mean multiplicity of 4 or 6. I mean, that's possible, but usually it's 2. In my head, the way I think of it, so just kind of a, like, how do I make sense of it? I think of it as like if you have a parabola and it's crossing and it's like you just keep getting closer and closer until finally you're bumping, you're bouncing off, that essentially these 2 roots get closer and closer and closer together, and it counts twice. It counts once for the coming down and again for the coming up. So that's how I just picture it, like why it makes sense to me. Like, oh yeah, sure, that's 2. I just kind of picture that progression there. Okay. So a summary of what we have covered in this lesson and what is probably useful stuff. The total number of roots equals the degree. Okay, so whatever the highest exponent is, that's how many roots are in play. This takes complex roots and roots with multiplicity into consideration. So you won't necessarily be able to see all of the roots on the graph. You will see the real roots on the graph, but you won't see the complex roots. And the multiplicity you can usually figure out or take a good guess based off of whether it bounces off the graph. Real roots will be x-intercepts on the graph. So if all you need are the real roots, the graph is probably the way to go. Complex roots always come in pairs, always, always, always. So when you're dealing with the things with the eyes in them, make sure that you always have 2 of them or 4 of them, 6 of them. And then some tips here, try graphing to find the real roots first, depending on the kind of question that you're asked. So if it's a multiple choice question, like what I would do is I would look at my answer choices and see what I was looking for in terms of real roots. And then I would graph it and then match up the real roots I could see on the graph with the real roots that I see in the answer choices. And you can probably eliminate at least 1, maybe 2 options with that, maybe like all 3 or 4, like however many choices you have. Then if you can kind of take it from there and you could look at things like multiplicity, things like that. After that, you would use polynomial division to reduce the polynomial down to a quadratic once you know what the real roots are. So this used to be like kind of navigating around polynomials like this. It used to be a big deal. You had to use something called the rational roots theorem to generate possible real roots and then do polynomial division 1 at a time until you found ones that worked. And you would just slowly make your polynomial smaller and smaller and smaller with the division until you got it down to a quadratic. And then, kind of take it from there. But we do not need to do that anymore. So now we can graph it and find the real roots. But if we do need to find the complex roots, we usually do need to do some polynomial operations in order to get the rest of the way there. Now, as I said, this used to be a common skill. It's not taught in as much detail now. So finding the roots of polynomials is one of those things that does come up in Algebra 2. It might reoccur in a pre-calculus class, but at no point really in your higher level math is somebody going to give you a polynomial and say, hey, you've got to find all the roots to this. If they do, it's a really rare thing that you would have to do. So that might make you feel a little bit better about this topic. It is something that is good to know about polynomials. It is also kind of a relic from before we had graphing calculators, and you would need to know the roots in order to sketch a graph, is kind of where it comes from. So you would use your end behavior stuff to get the ends, and then you would go through this process to get all the intercepts, and then you would sketch a graph using all that information. But graphing calculators does kind of render it to some extent an obsolete skill. Please don't forget to like and subscribe if you found this video helpful. Drop a comment or question to engage. Check out the practice set to test your skills from this lesson, and check out the other videos and playlists on the channel. Hope to see you in a future video.